What's up, kids? Mr. Gustin. I'm not in the physics classroom. I'm here at home because of the power outage, but I wanted to make sure that I had an opportunity to walk you through problem 2 on practice problems number 6. Okay, we kind of rushed through it in class, but I wanted to give you an opportunity to really discuss probably 2A through E. It's the mathematical portion of the problem. Okay, we discussed a little bit, so I'm going to kind of breeze through the first part, but we'll really hit on that math, that algebra stuff that might be confusing for some of you. So, again, practice problems number 6, 2. Let's start by drawing our picture. Of course, we read the problem. The very first thing we always do is we draw our picture. There's my cylindrical pulley. There's my bucket. Here's my axis of rotation. In class, we talked about there being a force of gravity, a weight force on the bucket. There's a tension force that we know is smaller than the weight force. Why is it smaller? Because the bucket's going to accelerate downward, so the downward force must be winning. In this case, that's the weight force of the bucket. Now there's a string. That string is attached to this pulley also. Because that string is attached to the pulley, and it's the same string that's attached to the bucket, that tension force on the bucket and on the pulley are identical. They are the same in magnitude, opposite in direction, not a third law pair, but they are opposite direction, same in magnitude. There were some other forces we had on the pulley. There was the weight force of, I'm going to call it C for the cylinder, and there was this upward normal force on the cylinder, balancing out those downward forces. Because that pulley is stationary, it's not accelerating, we know that the net force must be 0. That was the first part of the problem, identifying all of the forces. The next part of this problem was to figure out, question 2A says, is the bucket's acceleration equal to g, less than g, or the same as baby g? Well, that's talking about acceleration. So let's go ahead and write a net force expression for the object moving linearly. That's the bucket. Let's go ahead and say the mass of the bucket times its acceleration is equal to the force of gravity, or mg, downward, minus this tension force. So the question, can A be equal to G? No, it can't be. There are two forces over there. All right, so if this is mg and I'm subtracting another force away from it, I know that the acceleration of the bucket must be less than baby g, because there is an opposing upward tension force on it, preventing it from being in free fall. That's the first thing, okay? Then we move on to question B. Question B says, determine the acceleration of the bucket. No problem. I already have my F net expression. Let's go ahead and just solve for A. I know the mass of the bucket is 4 kilograms, so I have that there, and I'm going to label that mass of bucket. I know baby G, 9.8, always. I don't know tension force, so now I'm stuck. I have this problem. I've got my net force expression with an unknown acceleration and an unknown tension force. Two unknowns. In math class, that means I need 2 equations. So what other equation can I build from this scenario? Well, the bucket's moving linearly, the cylinder's rotating, and because it's rotating, I can probably write a net torque expression. So that's what I'm going to do. I'm going to write a net torque expression, so T net, for the cylinder. All right, let's look at the picture. What forces on the cylinder are producing a torque? What forces are acting away from the axis of rotation and perpendicular to the lever arm, to the radius? The only force that's acting not at the axis of rotation is the tension force. So I'm going to go ahead and say the net torque is equal to Ft times the radius of the cylinder. That's a net torque expression. We also learned in class today, just like F net is equal to the sum of the forces and mass times acceleration, we learned that the net torque is equal to the sum of the torques, and it's equal to the rotational inertia of the object times the rotational acceleration, or angular acceleration, of the object. I've got 2 expressions now. I've got my F net and my T net. In class, we did a little finagling. We looked more at this torque net expression, and we kind of made it more useful for us. We said, okay, well, it's going to say, we'll say that T, the torque, the tension force times the radius of the cylinder is equal to I alpha. If I go look at my equation, not my equation sheet, my reference sheet for rotational inertia values, I see that I, for a cylinder, is 1/2 the mass of the cylinder times the radius of the cylinder squared. Got that for I. I also found out this cool concept, this idea that as the bucket accelerates downward, because it's attached to the string and the string doesn't slip, Because of that, as the bucket falls, it's going to pull on my cylinder. As the bucket falls, it pulls on my cylinder, which means the cylinder doesn't move unless the bucket moves. We would say their motions are like bridgeable. They're related, which means I can use a bridge equation. The acceleration of the bucket is very closely related to the angular acceleration of my pulley. Remember, the angular acceleration times r gives us linear acceleration. Or, in our case, acceleration over r is equal to alpha. Let's take that and plug it in over here since we're solving for acceleration anyway. So let's say angular acceleration is actually a over r of the cylinder. Okay, a little more useful expression there. There are some values that I can cancel out over here. Like this is r squared, and then it's divided by r, so I'll lose that r, I'll lose that square. I've got r on both sides of the equation. I'll drop those r's out. I'm left with this expression for tension. Ft equals 1/2 the mass of the cylinder times A. Okay. Now it's time to do some algebra fun. Let's just start plugging some stuff in. So I didn't know tension over here. Well, now I have an expression for tension. Let's rewrite my F net over here. Mass of the bucket times A equals mass of the bucket times G minus 1/2 mass of the cylinder times the acceleration of the whole thing. I guess I can start plugging some stuff in, but I've got A on both sides. I'm going to want to clean that up a little bit, so I'm going to rewrite it. Mass of the bucket times A. Oh, I messed up already. This is plus 1/2 mass of the cylinder times A. And notice, I'm keeping track of which mass I'm talking about. It's too tempting to forget about those subscripts and just cancel mass out. But they're different masses because they came from different expressions. One came from my cylinder and one came from my bucket. So keep those straight. This is equal to mass of the bucket times G. I isolate again. I get A times mass of the bucket, 1/2 mass of the cylinder, mass of the bucket times G. Acceleration is equal to mass of bucket times baby G divided by the mass of the bucket plus 1/2 mass of the cylinder. I plug those values in, and you can do this at home. You plug your values in, and I end up with 8.25 meters per second squared. That's my acceleration of the bucket. Let's double back. Let's check with A. I said it would be less than baby G, which is 9.8. Is it? Yes, it checks out. This answer makes sense. Is it totally right? I'm not 100% sure, right? If I'm a student doing this problem for the first time, I'm not sure, but it definitely agrees with my conceptual answer from part A. So it's not bad. It's not totally off. If I'm wrong, it's not that bad. I like that answer. That looks good. 2 equations, 2 unknowns. I work them out. I use a bridge equation, and I solve for my acceleration. That's 2B. How about 2C? Now 2C says if the well is 8 meters deep, determine the time it takes for the bucket to reach the bottom. Okay. And it says starts from rest. That's linear motion. Bucket moving linearly. Let's think linear kinematics. I'm going to erase all this, so stop it here, freeze it here, but we're going to move on to C. So I hope right now you're kind of writing out your variables. What are the knowns and unknowns you have for this picture? Let's think about the information it gives us. It tells, well, we know now that the acceleration is equal to 8.25 meters per second squared. The initial velocity is equal to 0 meters per second. I know that the change in y, or the displacement, is 8 meters. I'm solving for time. Let's think about this. I know acceleration. I know initial velocity. Oh, you know what? Acceleration, displacement, time. This is my quadratic. Change in y equals initial velocity times time. 1/2 gt squared. Why is it g? Oh, should it be g? I'm going in free fall? No, we're not in free fall. Don't get carried away. Yes, we are moving in the y direction, but no, we are not in free fall. Make sure you use acceleration. Change in y is 8 meters. Initial velocity, 0. 1/2 8.25 meters per second squared times time squared. You solve for time. I end up with, what do I end up with here? 1.39 seconds is my time. Okay. D says determine the rotational speed of the pulley at the bottom of the well. So after it's fallen for this long, determine the rotational speed. There are a number of ways you can do this, but the one thing that stands out to me is this. The one thing that stands out to me is if I find the final speed linearly, I know time now, it's 1.39, but if I go ahead and I find the final speed linearly, I can use my bridge equation. I can say omega times r equals v. I can use this to find angular speed. So let's try that. Let's try and find final velocity linearly and then bridge it over to angular. In order to find final speed, I know that final speed squared equals initial speed squared plus 2a, change in y in this case, that's 0. V final squared is 2 times the acceleration. We found that, 8.25. Change in y is 8 meters. I solve it. The final velocity linearly is equal to, I don't have a calculator, but you can solve that. What I'm going to end up doing with that value, though, is dividing it by r of my pulley, right? Make sure it's the object rotating of the pulley, and that will give me omega. Omega ends up being 57.33, not meters, we're talking angles, radians per second. Question E says, how many revolutions did the pulley make while the bucket was falling? That's like rotational displacement. Rotational displacement times r is equal to angular displacement. In this case, delta y. I could go ahead and use a whole different kinematics equation, or I could remember that I was given delta y. Let's just use our bridge equation. Delta theta is equal to 8 meters divided by the radius of the pulley. I end up with 39. I'm looking for how many revolutions did the pulley make. 3.9.85. This is my number of radians per second. You can go ahead and then divide that by 2 pi to find revolutions. Okay? F, G, and H are more conceptual questions that I want you to answer on your own, but this is the algebra and kinematics behind it all. The F nets, the torque nets, the kinematics, the translating between rotational and angular. This is what I wanted to show you. So obviously go back, watch as many times as you need. Email me if you got questions, and then go ahead and finish up practice problems number 6. Hopefully you do number 3 and number 4, but do your best answering these questions, all right? See ya!